Hello Math 125 fans, let's continue on and do just a couple examples of trig substitution. There's no way I can hit everything. You can find a lot of other resources where I talk about this, but it's this clever idea of using a trig identity to make a square root go away. So I always want to make sure the students have this idea. There's a square root in this first problem. It's the square root of x squared plus 9. How can I make that square root go away? Someone long ago remembered, well, I do have these identities. It's a very clever, kind of pretty idea, which is we have this identity. So we can say things like cosine squared is 1 minus sine squared is 1 minus cosine squared, and that actually might be of help. What I mean by that is we have something that looks like this. So if we ever can get a situation where we have the square root of 1 minus something squared and we replace it with a sign, then we can possibly simplify it. Now there are some details about the domain and other things. I'm not talking about that here. So what are the other identities? Well, if we divide everything by cosine squared, we get tangent squared of theta plus 1 is secant squared. That gives us another idea, which is if there's a plus and a square, boy, it might be nice I put a tangent here. And that's exactly what we have here. I would like a tangent there. Now, if you just put a tangent there, it's not going to simplify because you're not going to get tangent squared plus 1. You're going to get tangent squared plus 9. So how do we make it tangent squared plus 1? And that leads to the method. So the method is we are going to replace x with 3 tangent of theta. So it's a crazy method to make things uglier. It's a substitution where we're not making it nicer in terms of the variable, but we're doing it to get rid of the square root. Okay, so let's run through how that goes. So we'll do the following. The whole reason we do this is this. So I tell students to do it in the margins. So we're about to do the square root, and I'll go through it. After you do a couple of these, it should really become second nature, but I'm going to square this because I'm plugging this in here. So 3 squared is going to be 9, and then there's going to be tangent squared of theta plus 9. The whole reason we did that 3 is because now it's going to become 9 tangent squared of theta plus 1. And the whole reason we did that is that now it's going to be 3, that's the square root of 9, secant squared of theta square root. And in the appropriate domain, and this is a bigger question that you could spend more time on in this section, because truthfully this should be 3 times the absolute value of secant. But if we know enough that we know it's positive, for now I'm going to assume we're on a domain where secant is positive. So there's this little subtlety right here. But what are we left with? So the biggest problems I see are then getting all of this information into here. Okay, so we're going to assume that it's 3 secant of theta. But where does all that go in this story? So lately I've realized that so many people make mistakes in this substitution that I've started to encourage students to actually write the square root. Meaning this is a wasted step. I wouldn't do this myself. But if it's hard for you to see where things go, and if you're prone to errors here, this is the same as this. You always want to pause when you're doing a substitution or change. That's not a time to hurry. Okay, what about dx? That's the other thing people forget because they're always like, oh, I made it through this other part, so I'm going to forget the derivative piece. Well, that's going to be 3 secant squared of theta d theta. And that's the idea of this section. So this whole integral becomes 5 over, the denominator is going to be 3 secant cubed. So it's going to be 3 cubed or 27. I'm just going to write 3 cubed. And then there's going to be a secant cubed. And then this is going to go here. 3 secant squared of theta d theta. That's the main idea of the section. So if you hadn't caught on to that, that's the point, is to get rid of that square root. Now let's go a step further, sort of finish this. Then things simplify, and it turns it into a trig integral. So there's going to be a 5. I think there's going to be a 9 because one of the 3's cancel, but that still leaves 3 squared. And there's going to be a 1 over secant. But what's 1 over secant? It's cosine. So this is definitely an exam question because it came out nicer than the homework. This is going to be sine of theta plus c. There's always these 3 phases. There's the substitution, which we did. That always takes about the same number of steps. There's the integration, and that's the part that could take really long. It just depends on what trig integral we get, but this one luckily was short. And then there's the returning. Interesting because my daughter's in a sophomore in high school, and she was just doing this, and she did not want to listen to me explain about this. But they just were being introduced to trig in her class, and part of the exercise was this: if I tell you that tangent of theta is x over 3, this was actually one of her homework questions. What is sine of theta? So likely you've all seen this at some point, but it's not something you probably have used very often. And I'm getting this from here. There's a way to directly go between those two without having to do inverse tangent or anything. And it's drawing a triangle. So if you think of this as a triangle, as a ratio, you can draw an example of a triangle where the ratio of the opposite and the adjacent is x over 3. And the moment you have that, then you can solve for the third side. Now with practice, you can just immediately solve it, but it's going to be x squared plus 9. And so this side is going to be the square root of x squared plus 9. Now I often tell students that should look familiar from earlier in your problem. Don't assume it's the same, because sometimes if you've refactored, but that was here earlier. Anyways, now we know what sine is. There's just a little maneuver to allow you to go between trig functions. Sine is opposite over adjacent, which is x over so this is 5. I haven't been checking solutions, so apologies if I've made some typo here. I'm focusing on ideas, but I think I got it. Okay, so hopefully that gives you some of the key ideas there. Ooh, shrink it up. Wish I could do that in lecture sometimes. I guess I could if I just knew how to. In lecture, I like to write with, on paper. But maybe I should do it this way. Okay, let's try this one. This one has a quadratic under a radical. So I'm thinking trig sub, but it has this unfortunate term in the middle. We need to complete the square. Now I find that there's like a super uneasiness about completing the square. So I tell students, if you ever forget completing the square, you're down the road in a future course, and you suddenly realize you have to complete the square, you could just run a little experiment. That's what we mean by a perfect square. If you do a perfect square, the middle term is 16x, and you could just expand it out. And then you could do the following: erase, erase, and try to figure out what's here. In completing the square, that's what we're doing. So you go, oh, this came from here and it was double. So I need to do half of this. And then I need to square it. So the technique is half the middle squared. You can remember this. This is if the number in front of x is 1, but if it's not a 1, I just factor it out, and I still use this method. So the number we want is half the middle, which is 3 squared, which is 9. Unfortunately, there's not a 9 there, so we do that little weird trick of putting a 9 in and subtracting a 9. So this is just one of those situations where you want to pause. When you are done completing the square, you should have a perfect square here and something else left over. And I like to sort of think, okay, I'm not ready yet. I'm going to collect all my thoughts. I'm going to rewrite my problem. Over here, I'm going to think about this for a bit. You just don't want to move on if you're unsure, but there is no reason to not quickly check and then ask yourself, is that the same as that? It is. I'm ready to move forward. Okay, so really need to make sure you pause and think about that. All right, 1 over x plus 3 squared. So you should know if there's been an error right now. You don't want to go further. And I probably did. These are the examples where I then realized, oh, I did make an error, but I don't think so. I checked my work. Okay, now we just do another one of these problems. Now you can do this in 2 steps, do a substitution for x plus 3. But I just like to go straight for it. X plus 3 I'm going to replace with what? I'm going to replace with the thing that would do blah minus 4 and get rid of the square root. So which identity looks like that? It's not sine because sine has 1 minus sine squared equals cosine squared. And that's not quite the same. So which one is it? Something squared minus 1 is equal to tangent squared. It's secant. I want a secant right there. But I need it to be a 1, so I put a 2 secant here. That's what I'm going to do. So if you understand the method, you can immediately do that. And this is going to simplify to 4 times secant squared minus 1, which is going to be tangent squared. Okay, so when all is said and done, I'm skipping a little steps here because I'm getting tired. Oh no, it's 2:30 in the morning. I just don't know if I can get these videos done if I don't stay up late to do that. But I also need the derivative. Dx is 2 secant of theta, tangent of theta, d theta. So we have 2 secant of theta, tangent of theta, d theta. Cancel, 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 cancel. The integral of secant. Now that's something that's in your table. It's not the one I use every day, but it's the log of secant plus tangent. Let me know in the comments if I've done it wrong. I might have needed my note sheet there. But secant is x plus 3 over 2, and then challenge yourself to figure out what tangent is. Secant is 1 over cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. Then can you solve for the other side? This squared plus that squared equals that squared. So x plus 3 squared minus 4 equals the other side squared. So it's this square root. So we have, and there's this other issue of the fact that there's actually a lot of ways you can write your answer. You could even re-expand if you just were tired of writing those parentheses. Plus c done. Okay, I think that's enough. We could spend a lot of time here, but I just wanted to, I'm focusing on principles. Do you understand the ideas? And I hope that's helping.